Very good morning, student. This is Rahul Garg, your maths teacher. Student, in last class we have discussed Euclid division algorithm and Euclid division lemma. And today we will discuss the numericals based on Euclid division algorithm. So first we will discuss what was Euclid division algorithm. You know that if we have two numbers, say a and b, then there must be q and r which satisfy the condition a equals bq plus r, and the condition for r will be greater than equals 0 but less than b, and a is greater than b. This was given by Euclid division lemma. Now we have already discussed the steps involved in finding the HCF using Euclid division lemma. Now our numerical is find HCF of 135 and 225 using Euclid division algorithm. Here 225 is greater than 135, so 135 is divisor and 225 is dividend. Divide this, we will get 135 and 90 as a remainder. And we know that we will follow the step until we will get our remainder 0. So again, now the Euclid division lemma will be applied on this remainder and this divisor, and divisor is greater than remainder, so divisor become dividend. Now again this will be on 1 and the remainder will be 45, but remainder is not 0, so apply again Euclid division lemma. This is 90 and 45 to the 90, and the remainder is 0, and now the remainder is 0, so this HCF, this 45 is HCF, so the HCF is 45. You can do in this way or the way which we have discussed earlier. In this we have discussed that if a is greater than b, then we will write a equals bq plus r. Now our number is 225 greater than 135, so our step 1 will be, first step will be 225 equals 135, our quotient 1, that is 1, and remainder becomes 90. Now remainder is not 0, so we will apply Euclid division lemma to 135 and 90. I will write 135 here and 90 here. This will multiply with quotient 1 and the remainder will be 45. But again the remainder is not 0, so we will apply Euclid division lemma on 90 and 45. 90 is written as dividend, and 45 as divisor into 2 plus remainder becomes 0. Now the remainder is 0, so this 45 is written as HCF. Our highest common factor is at 45. स्टूडेंट, अगर हमें दो नंबर का HCF फाइंड करना है तो हम क्या करेंगे, सबसे पहले चेक करेंगे कि विच नंबर इज ग्रेटर, और उसके बाद हमारे पास दो मेथड हैं, दोनों के दोनों मेथड सही हैं, जैसा आपको सूटेबल लगे आप वही मेथड प्रेफर कर सकते हैं। दोनों ही यूक्लिड डिवीजन लेमा को फॉलो करते हैं। बस ये है कि ये डिवाइड करना इजी है, अगर आपकी कैलकुलेशन अच्छी है और आप इसको डायरेक्ट लिख सकते हैं तो आप इस मेथड के लिए भी इस मेथड से भी कर सकते हैं। जैसे यहाँ पे हमने क्या करेंगे, सबसे पहले जो नंबर ग्रेटर होगा उसको डिवाइज़र, और जो स्मॉलर होगा वो हमारा जो स्मॉलर है वो डिविडेंड बन जाएगा, और जो ग्रेटर वाला है वो डिवाइज़र बन जाएगा, और सिंपली डिवाइड करते रहेंगे, और जब तक हमारा रिमाइंडर क्या ना आ जाए, ज़ीरो ना आ जाए। यहाँ पे भी हम सेम ही चीज़ कर रहे हैं। देखिए सबसे पहले 2 2 5 1 3 5 एंड 1 और रिमाइंडर 19, अगेन 90, this 135, this quotient 1, this 45, remainder here. Both are the same things, but the difference is only the way of writing. In this we are writing in the format of the statement, but in this we are doing the division. Okay student, now our second sum is show that एनी पॉजिटिव ओड इंटीजर। स्टूडेंट यहाँ पे ओड लिखा हुआ है, ध्यान रखना। शो दैट एनी पॉजिटिव ओड इंटीजर इज ऑफ द फॉर्म 6q plus 1, 6q plus 3 और 6q plus 5 where q is some integer. नाउ स्टूडेंट हमें यूक्लिड डिवीजन लेमा को ही फॉलो करना है इसे प्रूव करने के लिए। तो यूक्लिड डिवीजन लेमा के अकॉर्डिंग हमें दो नंबर चाहिए सबसे पहले। तो हम क्या कर रहे हैं, लेट ए बी एनी पॉजिटिव इंटीजर, ए बी एनी पॉजिटिव इंटीजर एंड b equals 6. I am writing this b which is given. If there will be given 3q plus 1, then I will let b equals 3. Now b is 6. Now apply Euclid division lemma. Apply Euclid division algorithm. Now Euclid division algorithm says that a equals this b, that is 6, and two number, that is q and r. What was the condition for r? R should be greater than equals 0 but less than b, and here b is 6, and the possible values of r is, and we are discussing only integers, so r is 0, 1 2 3 4 5, because r should be less than 6 but greater than equals 0, so 0 1 2 3 4 5. These are the possible values of r. Now we can write a equals, if my remainder is 0 then it becomes 6q, or if my remainder is 1 then it will become 6q plus 1. Similarly 6q plus 2, 6q plus 3, 6q plus 4, 6q plus 5. These are the possible values of a, and a is any positive integer. We have assumed that a is any positive integer. Now if we will check 6q, then we can write 6q as 2 into 3q. Similarly 6q plus 2 can be written as 2 common 3q plus 1, and 6q plus 4 can be written as 3q plus 2, and these terms are multiple of 2, hence 6q, 6q plus 2 and 6q plus 4 are even number, because they are the multiple of 2 are even number. But according to statement we want odd integer. Now check our remaining term, that is 6q plus 1. Now 6q plus 1 can be written as 2 into 3q plus 1, means 2k1 plus 1. Similarly 6q plus 3 can be written as, if we write this as 6q plus 2 plus 1, then 2 will be common out. It becomes 3q plus 1 plus 1. Means 2k2 plus 1. And 6q plus 5 can be written as 6q plus 4 plus 1. And when we will common out the 2, then it will left with 3q plus 2 plus 1. And if you see, these are the odd numbers because 2k is even number, and if we add 1 in even number, then it become odd number. Similarly, this is also odd number and this is also odd number. So we can say that any positive integer and 6q plus 1, 6q plus 3, we can write a in any these of the 6 terms. But if we want to write odd integer, then this can be written in the form this: 6q plus 1, 6q plus 3, 6q plus 5. So any positive odd integer can be written in either of the form, that is 6q plus 1, 6q plus 3 and 6q plus 5, where q is any positive integer or any integer. Q is integer. Now our third sum is use Euclid division lemma to show that square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. So first, let us say any number let a be any positive number, integer, and b equals 3. Now apply Euclid division lemma. We will get a equals 3q plus r, where r is less than 3 and greater than equals 0. And the possible value of r are 0, 1, 2. So we can write a as 3q plus 1 and 3q plus 2. I substitute the value of r, that is 0, 1, 2. When we will put 0, that it become 3q, and when we will put 1, it become 3q plus 1 and 3q plus 2. Now in statement this is said that it is said that the square of any positive integer, so take square of a, it will become 9q square, and the square of 3q plus 1 becomes 3q plus 1 square and 3q plus 2 whole square. This is 9q square, and here we will apply identity a plus b whole square. This will become 9q square plus 1 plus 6q, and this will become 9q square plus 8 plus 12q. Now this is our a square, and a square, this can be written as 3 into 3q square, and when we common out 3 from this becomes 3 into 3q square plus 2q, and this one as it is. And now apply here, this will become 9q square plus 12q. I write 8 as the form of that is the multiple of 3. Sorry, here this will become 2 to the 4. We will divide this form 4 as 3 plus 1, so that we can common out from this 3, because we have to write this in the form 3m or 3m plus 1. Now this is 3, and let this is k1 and this is k2, and this will, when this will be common out, we will take common out from 3. This will be left with 3q square plus 4q plus 1, and this plus 1 as it is, and this is 3k3 plus 1. Now k1, k2 and k3 are some positive integers, where k1, k2, k3 are positive integer. So all these are the same form, that is 3m or 3m plus 1, because this is also 3m plus 1, this is 3m plus 1, or this is 3m. So square of any positive integer is either of the form 3m or 3m plus 1. Okay student, thank you student, and have a nice day.